Hello, I am Vincenzo Madaghiele, and today I will present our paper, which is called Experimenting Techniques for Sonic Implicit Interactions, a real-time sonification of body textile heat exchange with sound-augmented fabrics. This work was developed in the context of the Sound for Energy project here at KTH in Stockholm. In this project, we are investigating different ways to raise awareness towards energy consumption in the home using sonic interaction design techniques. The theoretical background for our project comes from the studies about digital interfaces for the home in the fields of human-computer interaction, sonification, and sonic interaction design. As argued by Gaver, digital technologies were originally devised to be used in laboratories and workplaces. Their design is therefore usually focused on efficiency and productivity. Several authors in HCI recognize the need for different priorities when designing for the home, suggesting the development of interfaces that encourage creativity, playfulness, and wonder, or that can operate at the periphery of attention. Such as, for example, the idea of calm technology by Weiser and Brown. These aspects can be related to recent studies on interaction design for energy in the household, such as the work of Strangers about home energy interfaces. In our work, we explored the concept of implicit interaction, which are interactions that are not explicitly initiated by the user, and the potential of sound to develop them. Following these premises, we developed the first prototype of a sound-augmented blanket that sonifies real-time heat exchanges between the fabric and the body. This aims to inform about energy that is not usually quantified by sensors in traditional digital systems, but that is indeed contributing to heating the body in a significant way, and therefore to energy savings. Generally, what we are interested in with our project is the potential for sonic augmentation of regular household objects, such as fabrics, to communicate energy-related information in a non-intrusive and creative way. Specifically, in this paper, we present the technical development of our artifact, the sonic interaction design techniques that we employed, and the results of our qualitative evaluation of the first prototype. Here is a short demo of the experience with our sound-augmented blanket, showing how the sound changes in relation to temperature, and how sound is at the same time used as a medium of interaction. Having decided to work on sonic augmentation, we used the natural sound of the body against the fabric as a primary acoustic material for our sonification models. To pick up these sounds, we used a piezoelectric contact microphone, which was tightly stitched to the fabric as an audio source. The audio signal from the contact mic was then sent to a Bella Mini microcontroller, on which the sound design models were coded in the pure data programming environment. Temperature data was collected with a simple LM35 sensor, and the output sound was played on a small 4-ohm speaker after being amplified. All of these components were stitched to the normal blanket that you saw in the video demo. I will now describe the two alternative sonic interaction models that we developed. The two models are different both in terms of interaction techniques, which means that the sounds are triggered in different ways, and in terms of sonification of data, which means that different timbral characteristics of the sounds change in relation to the temperature which is registered by the sensor. Our sonifications were inspired by recent research done at IRCAM about semantic connotation of sounds. We tried to give characteristics of a warm sound, such as low pitch and spectral richness, to high temperatures, and of a cold sound, such as higher frequency components, to the lower ones. The first sound model is based on a granular synthesizer, and here is a demo of the interaction with these models. So when the temperature is low, the sonification sounds like this. And when the temperature is high, it sounds like this. The second sound model is instead based on an envelope follower, which activates a bank of sawtooth oscillators with different tuning ratios. Here, the warm character of the sounds is achieved by increasing the amplitude of different frequencies. So here you can see a short demo of the interactions with this model. And now the difference between cold and warm. This is cold. And this is warm sound. After developing the prototype, we devised a qualitative evaluation procedure, which was aimed at understanding different aspects of the experience before our next design iteration. Specifically, we aimed at understanding how people approach the sonic augmentation of a common object at their first interaction with it, how the sound response changes the affordances of the object, and the characteristics these interactions should have to be implicitly understood. To do so, we developed a qualitative evaluation in which participants were free to explore the artifact as they wanted, with the two different sound models. Participants were 6 PhD researchers in our division, 3 women and 3 men. The initial reflections from our evaluation point to the fact that different people approach the object in very different ways. In general, two main approaches could be recognized. Some people approached the artifact as a blanket and were using it as they would with a regular blanket. And others were interested in the sound-making capabilities of the object, approaching it almost as a musical instrument. The sonic characteristics of sound model 1 and 2 afforded very different movements, with model 1 encouraging ample gestures and model 2 stimulating repetitive and less demanding interactions. The connection between the sound and the temperature was not very clearly understood by participants. Moreover, the ambiguity of the prototype in terms of function was frustrating for some participants, who asked for clarification about the intended use case scenario of such an object. For others, instead, the ambiguity was interesting. So, to conclude, the sonic augmentation techniques were successfully responsive, and sonic augmentation radically changed the perceived affordances of a common blanket. The aspect about sonification of data needs further investigation and testing, specifically about the clarity between which aspects of the sound are modified by the movement and which are influenced by the temperature. Overall, though, the blanket was successful in sparking curiosity and developing a range of simple and very personal aesthetic experiences by participants. Thank you for your attention, and for those interested, you can find the code for the project on the link on this slide and in the paper. We are looking forward to your questions.